So we continue our study of internal forces. Thus far, we've just dealt with tension and compression. If we have loads that are applied but not at the joints, then we'll also get shear force and something called bending moment. So here's a beam. We're asked to consider a point 3 meters from the pin joined at A, and to find the tensile force, this new idea of a shear force, and another new idea called a bending moment at this point here, 3 meters from the pin. We start with external force analysis, which is identical to what we've already done. So we draw the support forces, and we recognize that at the pin there could be a y component and an x component, and then over here at the roller there's just a y component. And we apply the conditions for equilibrium. So summing x forces to 0, we've got positive ax and positive 100, so clearly ax will be to the left and 100. Summing y forces, we've got upwards ay, upwards by, downwards 200, and those sum to 0. So that can't be solved yet. We'll need the moments equation. Let's sum moments about A. So we've got a 200 Newton force 5 meters away. That's an into the page negative moment. And then we've got the By force with a positive moment acting 7 meters from A. Solving then, we find the components of reaction at the supports. We solve for By using the moment equation. It's 142.86. These are all in Newton units. And then we can finally solve for Ay. That's 57.14. These are all in Newton units. Okay, so that's the first step. Analyze the external forces as. Now we'll analyze the internal forces. So the first thing to do is to make a section at the point of interest and then draw the internal forces. So our point of interest was 3 meters from the pin A. Now at that section point, the internal forces will be as follows. First of all, there will be tension, and that acts along the structural member. And by convention, we assume that all members are in tension, and we use an N for the tension force. So here I've split apart the beam at the section point, and so we have a tension force N, and that's what this little arrow is here. Okay, and obviously we still have the AY and AX forces here. They're still acting at the point A, AY, and AX. Now, in addition to tension, because this load isn't applied at a joint, it's applied somewhere in the middle, we also get a sideways force, which is known as shear. Now, if we push down on this beam, or even if this beam was just loaded by its own weight, it's going to tend to sort of sag downwards like that, and that means this side is being pushed down by the other side. So shear on the left side is taken to be downwards by convention, and the symbol that we use for shear is V. Now we should remember, of course, that the law of action and reaction prevails, and so there's actually reaction forces over here on this side that are opposite in direction. So there'll be a tension force that way and a shear force that way, and we'll just sort of pencil those in, because although we're not analyzing the equilibrium of this piece here on the right, we could, and we'd get exactly the same answer. All right, so those are two internal forces, the members in tension, and there is potentially a shear force. And the shear force, by convention, is taken to be downwards on this element. Now, we're not done with internal forces for the following reason. We said that that beam would tend to sag under its own weight. If it were to do that, then there's going to be a little bit more deformation here at the bottom surface than there is at the top. That means there's more tension here at the bottom surface. Now, this sagging has been grossly exaggerated in the picture. In reality, you wouldn't be able to detect it by eye, but the tension will indeed increase in a simply loaded beam from top to bottom. We're going to represent that non-uniform tension by an average tension, and then to indicate a little bit more tension at the bottom, we've got a little extra force to the right, a little less tension at the top is a force to the left. We see that this is actually a couple. So our equivalent then for this non-uniform tension will be an average tension, that's what we called before N, and this couple moment M, which is known as the bending moment. So we can now finish up the force diagram and analyze the equilibrium. And so here's the force diagram from before, where we had AY and AX, the pin reaction components. Then we've got the tension N, the average tension N, the shear force, which is taken by convention to be downwards, and then we've got this bending moment M, a couple moment, which acts here at the section and is represented by letter M. So now we apply the conditions for equilibrium, as we've done many times so far in this course. And we sum x forces, and then we've got AX to the left, negative 100, plus the tension acting at the point X is 0, summing y forces. We've got upwards AY, which was 57.14, and then we've got downward shear, so that's 0. Then we'll sum moments, and moments are typically taken about the section point, because then we don't have the unknown moment to deal with due to the shear force. So we'll sum about the point X, and about that point there, we only have a moment for AY, and it's going to be a clockwise negative into the page moment. And that force is acting 3 meters from the point X, and then obviously we have our bending moment, which is a couple of free vector. And yes, so that needs to be accounted for in the moment equation. So there we have it, solving then for those internal forces acting at the point X. Clearly we have 100 newtons of tension, we've got a shear force that's 57.14 newtons, and then solving for our bending moment, we get 171.42 Newton meters. Okay, so that's the internal forces at that point, 3 meters from the pin. Now notice that there are reactions acting on the XB segment. So the AX segment would tend to pull the BX segment to the left. If the AX segment is pushed down, then the BX segment is going to be pushed up. And for this positive reaction moment, there will be a negative reaction moment over here. Just let me draw that. Pause and draw. Okay, so there it is right there. So, yes, action-reaction pairs. There are these internal forces and moments. Now, the reason I mention that is because if you analyze the equilibrium of this piece, you better get the same answers, and it turns out indeed that you do. So here are the equations written out for summing forces and moments to 0, and you get exactly the same answer. So what we've got so far then is at this point X, 3 meters from the pin, this segment AX is pulled to the right, it's pushed down, and then it's also twisted. Right? There's a moment that acts at that point X, and those are forces internal to the structural element. Okay? And they are all due to the other side, what the other side, the XB segment, is doing to the AX segment. Now, let's repeat that, but instead of being 3 meters from the pin, now let's let the distance be a variable x. So the external reactions are exactly the same. It's still the same beam with still the same loading. And so we don't need to repeat that. That's already been done. The only thing is now we need to let that distance x be a variable in some way. Oh, well, let's draw the forces acting at the section. Now we're going to have to do 2 different sections here, because clearly something different is going to happen if we're over here than being on this side. So let's start with the distance x being less than 5 meters, and then we'll have those same 3 internal forces to consider, or 2 internal forces and 1 internal moment. So tension N, shear force V, and then a bending moment. It takes a minute to draw that. I'll pause the video. Okay, so there it is. So this is N, V, and M. Okay, so we'll apply the conditions for equilibrium. X forces sum to 0. Okay, that equation didn't change at all, given that we're a distance x. The y equation doesn't change either. There's a y. So we're going to get exactly the same tensile force and exactly the same shear everywhere on this side. What does change is the amount of bending moment. So we'll take moments about this point here, and then, so we've got, about that point, we've got an AY moment that's negative into the page, and that force is now acting a distance x away from this pivot point here. So when we solve this, we see that our bending moment now, well, our tensile force and our shear force are constant over the length of this segment. At least as long as x is less than 5, you have the exact same shear force and tensile force. But the moment, the bending moment, actually varies with the distance x away from A. So you're getting an increasing bending moment as you get out towards this point. Now let's go to the other half of the structure. Not the other half, but we'll let, excuse me, now consider a distance x that's greater than 5. So we're over here now. External forces, well, we still have the same y and x forces acting at the pin and the same support force acting at the roller B. Now let's consider our internal forces here. So this will be our tensile force, and this will be our shear force. And then, of course, there's a bending moment. Again, I'll just pause and put that on there. All right, so there's our bending moment, M. And now let's write out the conditions for equilibrium. So x forces sum to 0. So AX was 100 to the left, and now we've got tension N. But then we've also got this 100 Newton force, that point load, to account for. When we sum y forces, we'll have the AY force, upwards 57.14. We'll have a downwards 200 Newton applied force, and then we've got a downwards shear as well. So solving for the shear, we now have a different amount of shear force than we did earlier. Let's again take moments about this point here where we've cut it. So there's no moment from the shear force or from the tension. There is a moment from this 200 Newton force, and there's a moment from the AY force. The AY force acts a distance x away, and it's still a negative into the page moment. The 200 Newton force is acting a distance x minus 5. This distance right here is labeled on the diagram is x minus 5. And that is a positive out of the page moment. And then finally, we've got our internal bending moment, M. And those moments must sum to 0. So solving here, we get a shear force that has changed direction. We always assume that it's downwards. The fact that it's negative means that it's now acting upwards. Our tensile force is now dropped to 0, and our bending moment, when we solve it, we get a different expression now for x being greater than 5. Now it's customary to actually graph these. So we've got a couple of axes that are drawn here and scale them to length directly underneath the structural element. So this first graph will be a graph of shear force, and the shear force was 57.14 and constant as long as x was on this side less than 5. And then for this segment, it was negative 142.86, and all of that's in Newton units. So there's a graph of shear. The bending moment, again, we have piecewise function, and the bending moment on this segment was 57.14x. So this is the graph of bending moment. And then over here, it changed, and we had a negative slope, minus 142.86 x plus 1,000. Now, you'll have to confirm yourself that those two functions actually meet up when x equals 5. Pretty easy to do, just put 5 into both equations, show you get the same value. And then you can also confirm that this one goes to 0 when x is 7. Something else to notice is that the slope of the bending moment graph is exactly the shear force. Or, in more general terms, as we'll see later, it's the rate of change, or the derivative of the bending moment. Okay, so there's our first problem, a simple problem. Now it's time for you to do one. So here we've got a beam with a point load of 5,000 newtons, and that's applied right in the middle, and then there's two roller supports A and B, and our job is to find the shear force and bending moment as a function of distance from this end, kind of like we just did. The starting point, of course, as always, will be external force analysis to find out what the reaction forces are at the supports. Then you'll make a section on this side at a point X, draw the forces, internal forces, and apply the conditions for equilibrium. Then you'll make another section over here, a distance x from the left end, draw the internal forces, apply the conditions for equilibrium. So pause the video and then try this one on your own. Okay, so hopefully you worked your way through that. So here is external force analysis. No surprise, it's very symmetric. We find that each roller joint's taking half the load, 2,500 each. Make a segment on this side. Draw the internal forces, tension, shear, and bending moment. And we always draw them this way. These are the positive senses. Tension is positive downwards, shear is positive downwards, and bending moment is a positive moment out of the page. So here are the equilibrium equations when x is less than the midpoint. Solved. And you find again the bending moment increases with x. Then you make a section on this side. So this distance here is now x minus 2. X subtract 2. And then here's your tension force, shear force, and bending moment. Remember, the bending moment comes because the tensile force isn't uniform over the cross section. It's actually a little bit bigger on the bottom. So that gives you an average tension force, and a moment is being equivalent to that. So again, solving the equilibrium equations. Hopefully you found this. Then when you make the graph, here's the graph of shear force as a function of distance, and then here's the graph of bending moment as a function of distance. Notice again that the shear force is the derivative, or the slope, of the bending moment graph. So that's our analysis of internal forces, and then in class we'll pick it up at this point and we'll do some more, slightly more complex problems.